Hey everyone, and welcome back for another deep dive. Today we're going to be tackling, something you might not have heard of before. It's called homogeneous coordinates. They're this really cool math concept that gets used all the time, especially in things like robotics and computer graphics. And we've got some pretty interesting stuff to work with today. We've got a robotics lecture from YouTube, and then also some translated notes that we're going to dig into. So by the end of this deep dive, you're going to understand not just like what these coordinates are, but like why they're such a big deal.
Yeah, we'll definitely get into that. We'll talk about the theory behind them and then all the practical implications as well.
Awesome. Okay, so let's just jump right into it. So imagine we're building a robot and it needs to navigate the world using cameras. What's like the first challenge we run into?
Well, with cameras, they're really good at giving us angular information. They can tell us where an object is in the field of view, but they can't tell us how far away it is. And that's where our traditional Cartesian coordinates, X, Y, Z, kind of fall short, right?
Yeah.
Because we need some way to represent points that could be really, really far away.
Yeah, it's like when you're looking at a photo, right? You can see where things are relative to each other, but you don't actually know how far away anything is.
Exactly. So we need a way to capture that depth information mathematically. And that's really where homogeneous coordinates come into play.
Okay. I'm definitely intrigued. How do they work?
So basically imagine you take our familiar 3D space, our X, Y, and Z axis, and we add a fourth dimension to it.
Okay.
And this fourth coordinate acts like a scaling factor. And here's the really kind of magical part of it. By setting that fourth coordinate to 0, we can represent points at infinity.
Whoa. Okay. So we're already bending the rules of space here. So we can actually represent points that are infinitely far away. It seems like that would be super useful for like a robot that's trying to understand like its environment, right?
It is. It really is.
Yeah.
And the transition between Cartesian and homogeneous coordinates is actually really simple. So to go from a Cartesian point like XY to its homogeneous representation, you just add a 1 at the end. So it becomes XY 1.
Okay.
And then to go back, you divide the first two coordinates by that fourth one.
Gotcha.
And then that kind of normalizes it back down into a 2D space.
That's really clever. But robots have to do more than just like perceive points in space. Right? Yeah. They have to actually move around and interact with stuff. So how do homogeneous coordinates help with that?
That's where the real elegance, I think, of homogeneous coordinates comes in. And it's matrices.
Oh, yeah.
Remember matrices from like algebra?
Oh, yeah.
So with homogeneous coordinates, we can actually represent both rotation and translation in a single 4x4 matrix.
Oh, wow. So instead of needing like separate operations for rotating and for like moving something, you can just combine them.
Exactly.
That seems way more efficient.
It is. And efficiency is critical in robotics, especially if you're thinking about like real-time applications.
Yeah, for sure.
Like, let's say our robot needs to rotate a point 90 degrees and then translate it like 5 units to the right.
Mm.
We can do that in a single matrix multiplication using homogeneous coordinates.
Wow. Okay.
Which is much cleaner than what you'd have to do if you were working with Cartesian coordinates.
I'm starting to really see the beauty of this system. But with matrices, the order of operations really matters, right?
You're absolutely right. Matrix multiplication is not commutative. So if our robot performs those transformations in the wrong sequence, it might end up in a completely different location than we intended.
Yeah.
So getting that order right is mission critical.
That makes a lot of sense. So we've talked about using homogeneous coordinates to represent points. But what about other geometric shapes? Like, can we use them to represent lines as well?
We can. And lines are super important in robotics. Think about it.
Yeah, that's true.
They can represent the paths that the robot needs to follow, the boundaries it needs to avoid, or even the edges of objects that it might need to manipulate.
Yeah, so like understanding lines is really critical for things like navigation and collision avoidance.
Exactly. Now, in homogeneous coordinates, we represent lines as vectors, just like we did with points.
Okay.
And we also add a fourth coordinate to these line vectors as well.
I'm sensing a pattern here. Is there a reason why everything seems to get an extra dimension in this system?
It all comes back to that idea of representing infinity.
Oh, right.
Remember how we use the fourth coordinate to represent points at infinity?
Yeah.
Well, we could do the same thing for lines.
So a robot can use homogeneous coordinates to, like, understand lines that stretch out infinitely in its virtual world.
Exactly. Think about like an image of a road disappearing into the horizon.
Yeah.
That's a line at infinity.
Yeah.
We can represent that mathematically using homogeneous coordinates, and that's incredibly useful for things like path planning. and understanding the overall structure of the environment.
Okay, that makes a lot of sense. But we can do more than just represent lines, right? Like, we can actually perform calculations with them as well.
Exactly.
Yeah.
That's the beauty of it.
Yeah.
Like, for instance, let's say our robot needs to determine if two lines intersect. Now, in traditional Cartesian coordinates, you'd have to solve a system of equations to figure that out,
Yeah.
which can be pretty computationally expensive.
Yeah.
But with homogeneous coordinates, we can just use a simple dot product.
Really?
If the dot product of those two line vectors is 0, they intersect.
Wow.
If it's not, then they're parallel.
It sounds like homogeneous coordinates are all about elegance and efficiency.
They are.
They simplify these complex geometric calculations, and they make them a lot faster, which is super important for robots that need to make decisions in real time, right? Okay, so we've talked about representing points and lines using homogeneous coordinates, and we've even touched on how they can be used for things like collision detection and path planning. But I'm sure there's even more to this story, right?
Oh, yeah, definitely. There's a lot more we can do with homogeneous coordinates.
Okay, well, I guess we'll have to save that for the next part of our deep dive.
That sounds good. So welcome back to our deep dive into homogeneous coordinates.
Yeah.
Last time, we were talking about how efficient they are for representing rotations and translations. But there's another really important aspect of homogeneous coordinates that we haven't really touched on yet.
Oh, yeah, you're right. We focused a lot on robotics in that last part. What about computer graphics? I'm curious how these coordinates work in that context.
Yeah, great question. So think about how we perceive depth in the real world. Objects that are farther away appear smaller, right?
Right.
And that's something that traditional Cartesian coordinates actually struggle to represent.
Yeah, that makes sense. It's like if you were trying to draw a landscape on a piece of paper and you wanted to have a vanishing point, where things kind of recede into the distance.
Yeah.
You would need some way to make those objects shrink as they get farther away. You couldn't just use a flat grid.
Exactly. But with homogeneous coordinates, we can actually model perspective accurately. So remember that fourth coordinate we added? Well, it acts as a scaling factor, which allows us to create those realistic depth effects.
Oh, I see.
And this is what's called a projective transformation. It's absolutely essential for creating realistic 3D graphics.
Oh, okay. So that's how video games and movies make those incredible 3D environments. They use homogeneous coordinates to mimic how our eyes perceive depth.
Exactly. It's all about simulating that distortion of perspective, kind of like what happens when you use a wide-angle lens on a camera.
That's really cool. So we've talked about representing points at infinity. We've talked about using matrices for transformations. What else can we do with homogeneous coordinates?
We can also use them to represent lines.
Oh, right. Lines, of course. Lines. They're pretty fundamental to geometry. But why are lines especially important in the context of robotics?
Well, think about it. Lines are everywhere in a robot's world, right?
It's true.
They can represent the paths that the robot needs to follow, the boundaries that it needs to avoid, or even the edges of objects that it needs to manipulate.
Yeah, so understanding lines is really critical for things like navigation and collision avoidance?
Absolutely.
Yeah.
Now, in homogeneous coordinates, we represent lines as vectors, just like we did with points.
Okay.
And we add a fourth coordinate to these line vectors as well.
Okay, I'm really sensing a pattern here. Is there a reason why everything seems to get an extra dimension in this system?
Yeah. It all comes back to that idea of representing infinity.
Oh, right.
So remember how we use the fourth coordinate to represent points at infinity? Well, we can do the same thing for lines.
Well, okay. So a robot could use homogeneous coordinates to understand lines that stretch out infinitely in its virtual world.
Exactly. Think about an image of a road disappearing into the horizon. That's a line at infinity. And we can represent that mathematically using homogeneous coordinates.
Wow.
And this is incredibly useful for tasks like path planning and understanding the overall structure of the environment.
Okay, that makes sense. But representing lines is just one part of it, right? What's really cool is that we can actually use homogeneous coordinates to perform calculations with those lines.
Exactly.
What kind of calculations? Can you give us an example?
Sure. So let's say our robot needs to determine if two lines intersect. Now, in traditional Cartesian coordinates, you'd have to solve a system of equations to figure that out, which can be pretty computationally expensive.
Yeah.
But with homogeneous coordinates, we can use a simple dot product to get our answer.
Oh, really?
Yeah, so the byproduct of those two line vectors is 0. The lines intersect.
Wow.
If not, they're parallel.
That's amazing. It sounds like homogeneous coordinates are all about elegance and efficiency.
They are.
They simplify these complex geometric calculations, and they make them much faster, which is super important for robots that need to make decisions in real time.
Absolutely.
Okay, so we've talked about representing points and lines using homogeneous coordinates, and we've even touched on how they can be used for things like collision detection and path planning, but I'm sure there's even more to this story, right?
Oh, yeah, definitely. There are so many other cool things we can do with homogeneous coordinates.
Okay, well, I guess we'll have to save those for the next part of our deep dive then.
Sounds good.
All right, so welcome back to the final part of our deep dive into homogeneous coordinates. We've covered so much ground already, from like the basics of representing points and lines to the power of those matrix transformations.
It's been quite a journey for sure. And in this last part, I'm excited to really see how all of these concepts come together and some pretty incredible applications.
Yeah, you mentioned self-driving cars a couple of times. Can you kind of walk us through how homogeneous coordinates are actually being used in that field?
Definitely. So picture this. You have a self-driving car navigating a really busy city street. It's constantly gathering data from a whole bunch of different sensors, cameras, LiDAR, radar, all that stuff. And each of these sensors has its own coordinate system, its own way of kind of measuring the world, right?
So it's like having a team of observers, but they each have their own like perspective and language.
Exactly. And that's where homogeneous coordinates come in. They provide this elegant way to translate all those different sensor readings into a single unified coordinate system that the car's computer can understand.
So it's like creating a common language for all those different data streams.
Precisely. Once the car has that unified view of the world, it can then use homogeneous coordinates to perform all sorts of critical calculations. For example, it can determine the distance and trajectory of other vehicles, predict potential collisions, and even plan its own path to avoid any obstacles.
Wow, that's incredible. It's like giving the car this like super powered spatial awareness that allows it to navigate all these complex environments safely and efficiently.
Exactly. And remember those matrix transformations we talked about?
Yeah.
Those are crucial for things like lane keeping, parking, and even making smooth turns. The car can very precisely control its movements by applying a series of rotations and translations, all represented using, you guessed it, homogeneous coordinates.
It really makes you appreciate the complexity of what these self-driving car engineers are doing. They're basically teaching cars how to see and think in 3D space using this like incredibly powerful mathematical tool. So beyond self-driving cars, what other fields are kind of benefiting from homogeneous coordinates?
Oh, they're everywhere. You see them in virtual reality and augmented reality, creating those immersive 3D experiences. They're super important in aerospace engineering for modeling the movements of satellites and spacecraft, and even in fields like architecture and civil engineering. They're used for 3D modeling and structural analysis.
It's like a universal language of 3D space, and it's applicable across so many different disciplines. And to think, we started this whole deep dive with that simple question, how do we help a robot understand distance?
It's a testament to the power of mathematical abstraction. By just developing this system for representing points at infinity, we've unlocked this whole world of possibilities, from lifelike computer graphics to, like you said, the future of transportation.
So for our listeners who are now totally fascinated by homogeneous coordinates, what are some good resources for like exploring this topic further?
Well, a really good starting point would be to kind of revisit those linear algebra concepts, especially matrices. There are tons of online tutorials and videos out there that break down these ideas in a really accessible way. And for those who are feeling a little more adventurous, there are open source libraries for programming languages like Python and C++ that let you actually experiment with homogeneous coordinates and build your own 3D applications.
Oh, that's awesome. So there are lots of opportunities for like hands-on learning and exploration.
Absolutely. And the most exciting part is that this field is constantly evolving. Who knows what incredible new applications will emerge in the years to come.
It's like we've given our listeners this key to unlock a whole new dimension of understanding. They can look at all sorts of technologies now and appreciate not just what they do, but like the elegant math that makes it all possible.
I love that.
Well, that brings us to the end of another deep dive. I want to thank everyone for joining us on this journey into the world of homogeneous coordinates, and a special thanks to you for sharing your expertise with us.
It was my pleasure.
Until next time, stay curious,